So Fourier week. so it was only basically two equations in this class. There was just the block equation, vector differential equation, and then the Fourier transform. And Fourier transform, it's, every educated person should know about the Fourier transform. You can't sort of have a good general education. One thing about the Fourier transform, if you understand the Fourier transform, there's other transforms that are kind of like it. And so it's, if you can just get through one, it's a good thing. And so we'll just try to break in. So in general, what are we talking about? What is the Fourier transform? It somehow changes from something like time into frequency. And we're also going to talk about Fourier transform of images, in which case you're changing from space into spatial frequency. And then you can go back. You can go back from spatial frequency to space, or temporal frequency to time. So most people have some idea of what the Fourier transform is. Like if you look at, you're playing a music app and you see the little thing that's showing you a little thing of what frequencies are present in the signal. That's doing gazillion Fourier transforms it's doing like 100 Fourier transforms a second to sort of like decompose that audio signal into different frequencies. And so I had that sort of understanding of the Fourier transform. You take some chunk of something and then figure out what frequencies it contains. That's sort of a sensible thing. But I didn't really understand the Fourier transform. And our goal is to actually understand it to the point where you could actually program the slow Fourier transform. And until you can actually sort of like really write out a program to do something, you don't really understand all the moving parts. And we'll sort of like try to approach this through correlation, because correlation is a more sort of intuitive thing. You have a signal and another signal and you correlate them. The Fourier transform is very much like a correlation. It's actually more, it's a lot like 4 correlations, basically, exactly 4 correlations. So that's how we'll get started with it. And so the Fourier transform has this, e to the, minus I say I and write t. What is going on? Something like that. So we already talked about that, and one easy way of thinking of what that is, this whole thing, you can think of this whole thing as if it was basically just a 2-dimensional vector of length 1. So it's a 2-dimensional vector of length 1, and so it's got a real part and then, an imaginary part, 2 numbers, and a real part. So that's the x and the y component. And what is the imaginary part? Well, we know just from basic trigonometry that is going to be basically the sine of this angle. And what is the real part? The real part is just going to be the cosine. Let me get that out of there because I'm going to use up that space. So this is just going to be the cosine of the angle. And the amplitude of this thing up there is 1. So it's always length 1. And so you can immediately see there's a relationship between sines and cosines and that thing. And now, a lot of times at the very beginning it's bad enough to have sort of the imaginary unit up in the exponent, but then what about the negative? Well, just think of this as you could easily move that negative into the angle. So that's the same as that to the, it's the same as e to the I with the negative inside, negative phi, like that. And so what does that mean? That just means that e to the minus I something is just the minus angle. So this is, minus phi going that way, plus phi going that way. So that's all the minus means. It's It's just kind of going the opposite direction. The angle is going in the negative direction instead of the positive direction. So we have to understand this down to the fine details because that's the thing that's actually in the Fourier transform. So let's start off with the Fourier transform. And so a lot of times when you're writing a Fourier transform, you use a capital letter for something that has been Fourier transformed into the frequency domain. And so here's the thing that's, so there's our capital H, which is a function of frequency. And that, when you do a Fourier transform, what you get out of it is a complex number. So this is a complex number. It's not necessarily length 1. It could be length anything. But you get a complex number for each frequency. And so what about the F? The F is a real number. So frequency is a real number. So so there's a complex number H of F for every F. So what is the Fourier transform? So basically what the Fourier transform is you take some other function, meaning like something that has a value at each point, and you Fourier transform it. And when you do this process, you have to, for each single frequency, you've got to go to every point in the function that you're transforming. So each single frequency depends on every point in the function that's being transformed. And what is it? It's a sum. So an integral is just a sum. It's a sum, and we'll start it off sort of doing time and temporal frequency. So there's real temporal frequency, and we'll start off in sort of the infinite case. Let's just go across all time, which is totally impossible. But so that means sum across all time the following thing. So this means like if you're thinking of it in programming, you would say for each time do this. And so for each time do this for one frequency. So for one single frequency number, you have to go and for each time do the following. And what we're doing is take that function that's not Fourier transformed, which is a function of time, and then multiply it by this e business. So it's just e to the minus I 2 pi f t. Okay, so there's the problem. So you got like 1, 2, 3, 4, 5, 6, 7 symbols there, all jammed together. So what does that mean? Well, if we look, so what's the 2 pi? The 2 pi is because the frequency is in cycles per second instead of radians per second. So radians per second is, 1 along the circumference. And so there's 2 pi radians to get all the way around the circle. So that's why you have a 2 pi there. You've got f, which is cycles per second. So that's, cycles per second. And then you're multiplying by t, which is seconds. That cancels out the seconds, and you end up with cycles. And so what is cycles? Cycles is angle. So this whole thing here is an angle, a real angle. This real angle here is like 25 degrees minus 375 degrees, whatever. It's just an angle. Okay, and then last but not least, we're integrating over small chunks of time. So that means, for each time point, for each small chunk of time, we just multiply this by this. And then we're done. Sum the whole mess up, and you get the signal for one frequency. Now, whenever you look at equations like this, it's always important to, let's label. So this guy is a complex number, amplitude 1. this guy is also complex. So that's kind of a disturbing thing, because usually when you first think about the Fourier transform, you think about taking, say, a musical signal over a certain period of time and then decomposing it into all its different frequencies. That doesn't seem like a complex signal. That seems like a real valued signal. And so how is it complex? Well, it's just, it can always be complex. So any old signal can always be complex. And how do you do that? You just make the imaginary axis always 0. So what is a complex representation of a real signal look like? It just looks like something like this. It doesn't go into the imaginary axis. So here's the imaginary axis, there's the real axis. So say like at an instant in time, so here's an audio signal like this. So at some instant in time, say like like this time point, that's how you would represent it as a complex number. You would represent it as a number that just happens to have 0 for the imaginary part, for the y-axis part. And then, what happens if you've got a negative number? So like a negative number, what does that look like? Well, that just looks like a vector that goes along the y-axis that way. So how do we sort of turn our time signal coming out of our headphones to Fourier transform it? We just tack in zeros for the imaginary part. So the thing about a Fourier transform that can't be avoided is the complex part. So we'll try to sort of think about it just in terms of correlations of real numbers, but we're going to have to do multiple correlations. And so what's the first thing you do when you see something like this? You just look at all the indices so you see where stuff is going. So if we look at frequency, so we've got like frequency here, and we can see that there's a frequency over there. So for a given frequency, we'll be substituting that frequency in repeatedly into the right side. And then for our sum is over time. And so there's time up there, and you can see there's time up there again, and up here. So look at all so it's a very compact equation, just a couple symbols in it, but just make sure that we understand mechanically what it's doing. So mechanically what it's doing is you take a complex function, and then for each point in time, you multiply it by this thing. And what is this thing? Well, it's basically just sine and cosine of a particular angle. And what is that angle? Well, it's 2 pi times whatever cycles per second you're currently working on times whatever the current time is in your sum. And so we'll make just a diagram of what that actually means. So one last thing, that's a complex multiply. So as usual in math, we overload things. So it looks just like a regular multiply, but it's actually complex multiply. And this guy is a complex add. So complex add was easy. Remember, complex add was just like a vector sum. You just take a bunch of complex numbers as vectors, add them tip to tail. So that's an easy one. The complex multiply is harder. That's the one that I talked about right at the very beginning. There was like dot product, cross product, and complex multiply, which was like a different kind of multiply. And when I talked about it at the beginning, we talked about it, so how do you complex mult? There's 2 different ways of thinking of it. One is you can think of it, I have a page on complex algebra, just how complex numbers, how you multiply them, which you can sort of like a quick and dirty cheat sheet. But the way we multiply complex numbers is you multiply the amplitudes. And so in that respect, they act like regular numbers. Like whatever the amplitude is, you just multiply it by another amplitude of the other complex number to figure out what the amplitude of the result is, and then add angles. And so that's the most intuitive one, really, sort of the polar angle view. So you multiply the amplitudes and add the angles. And so that's why we can sort of think of complex multiplication as kind of a rotation, because you're adding the angle of the second complex number to the first complex number. But we can also think of it algebraically just with multiplications. So, and I wrote out like a funny looking method of doing it with a matrix. So you'd have like 4 numbers, and you turn one complex number into 4 numbers, and then you multiply that by another complex number that's a vector, and you get a third thing, which is a new vector. And if so you can look at, and how does this one work? Well, this one involves 4 multiplications. So you have to multiply, it's like the real of the first number times the real of the second number minus the imaginary of the first number times the imaginary of the second number. That's the real of your output. And then you've got to do the real times imaginary plus imaginary times real for the second number of your output. So you've got to do 4 multiplications and some additions. So 4 multiplications and 2 additions to multiply 2 complex numbers, whereas with regular numbers you just have 1 multiplication. So what are those 4 multiplications? So what does this imply here, this complex multiply? So if we write it out, what it looks like is we've got, whatever the real value at a particular point in time was, times the cosine of 2 pi f times t, that whole mess, plus whatever the imaginary value was at a particular time point, times the sine of the same thing, 2 pi ft, comma. And so that's 2 multiplications and an addition that tells us what the real number of that multiplication is. And then the second one is going to there's a minus in here because of that guy. So it's going to be the real times the sine, 2 pi ft, plus the imaginary times the cosine, 2 pi ft. And so this will be the imaginary number. So those two, so there's 4 multiplications total. There's 4 multiplications total. And so what are those multiplications actually doing? So what does it mean when we just multiply a pair of numbers, a whole bunch of pairs of numbers? Because remember, this is just how you calculate this complex output for a single time point. But the whole point is we've got to sum across all time. So what you're doing is you're fundamentally correlating. So you're doing, or you could also say you're doing a dot product. That's what a dot product is basically a correlation. And so what is a correlation? Correlation is like take a whole bunch of pairs of numbers, multiply them by each other, add them up. That's the meaning of a correlation. And so look at what you're doing. You're taking the real component of your signal and you're correlating it with a cosine at a particular frequency. We'll get to the particular frequency. And then you're adding that to the imaginary part correlated with a sine, and then that's real. Then you've got the real part correlated with a sine. We haven't done that one. That's the third possible correlation. Added to the imaginary part correlated with a cosine. We haven't done that one either. So you got you have real cosine, imaginary sine, real sine, imaginary cosine, all the four combinations. So that's kind of made life more difficult. We used to just be able to multiply. Now we've got to that's how we multiply. But let's start off with just considering a real signal. And so if we consider a real signal that's stuck down on the x-axis, it's a complex signal, but it's a special kind of complex signal that doesn't have any imaginary part. The imaginary part's always 0, and so the arrows just expand and along the x-axis, either go negative or positive on the x-axis. Then we can throw out these guys, because these guys will go to 0. 0 if signal real. So if we throw out those guys, then we can just concentrate on these guys here. And so that's what I'm going to draw. So you can see how we can calculate one frequency, one point in the frequency domain by examining all the points in the time domain. And so what are we doing? We're just basically taking so another way of saying this is we're just taking our real signal. So these are the same numbers. These are equal. So we're just taking our single real signal and we're correlating it with a cosine and then correlating it with a sine. So that's fundamentally what a Fourier transform of a real signal is. It's a little more complicated if you've got a complex signal, and when we talk about MRI, it's going to be a complex signal, so we'll eventually have to get there. But let's just start off. We're just going to claw our way in to just really understand what the Fourier transform is doing. And what it's fundamentally doing in the case of a real signal is it's just correlating the signal with sines and cosines. So let's draw that out. So we draw that out with a real signal. So here's our real signal. So this is our H signal at a particular point in time, just the real part of it. So our real signal. So, and if we think of that as something like something like this. So it might be something that's going into your headphones. What is going into your headphones is just a stream of numbers, like usually something like 40,000 per second. So 40,000 numbers per second just go into your headphones. And what do those numbers mean? They just mean what's the loudness of the sound every 1/40th of 40,000th of a second. And so here's all those numbers going into your headphones, and then it sounds like an orchestra or some kind of complicated sound. But it's actually just at any one point in time. So remember, this is time here. It's just one number. And since the Fourier transform insists on having a complex input, then we've just got a bunch of zeros for the imaginary part, so that we can avoid doing that second set of multiplications there. So here's our H function imaginary part. So this is imaginary signal. It's not imaginary at all. It could easily be another stream of numbers, real numbers. And here's the real signal. Okay, so that's our input to the Fourier transform. So now, and I've kind of sort of slightly sleazily gone over. We'll just go over, say, like 360 degrees worth of angle for our sines and cosines. And eventually, when we get to MRI, we're never collecting an infinite amount of time. And, you know, and on your little music app, that when it's making Fourier transforms and showing what frequencies are contained within each little chunk, it's running repeated Fourier transforms over little chunks of stuff. So we'll eventually get to a discrete Fourier transform where we just Fourier transform just a discrete amount of stuff instead of, you know, going over all time. But we don't want extra complication. And so let's just consider one cycle worth of, one 360-degree cycle worth of angle for our sines and cosines. And so now we've got to do this operation with the real signal. And so what does that operation look like? So if I make this go all the way down, because we're going to get the same size thing once we do our Fourier transform. So here's our sine and cosine. So what are our sine and cosine? They're basically just we've decomposed this imaginary number into the sine of that angle and the cosine of that angle. That's all it is. So this thing here implies two numbers, you know, like a real and imaginary part. And now we have to consider, so this is all 0 here. This is time going this way too. So this is time again going this way. And so now we have to consider this thing. It's got a bunch of stuff in it. So let's write out the cosine first. And let's do the example for the cosine of 3 for frequency. So we'll do cosine of 2 pi frequency times time, where we set f to 3. So go into MATLAB and just see what happens if you put, like, you know, cosine of 2 pi 1 and then plot that as a function of time, and then do cosine of 2 pi 2 times time, plot that as a function of time. As you turn the f up, what happens is you just get more bumps. If you put in 1, you'll just get a single sine bump. But if you put in 3 there, you're going to get, or a cosine bump, you'll get 3 cosines. And so let's just draw that. So here I'll put my signal in green. So let's draw that. So we're going to need 3 cosines. So and cosine goes between 1 and -1. So here's the first one, and then there's the second one, and then there's the third one. Okay, so that's cosine of 2 pi 3 times time plotted as a function of time. So just convince yourself when you stick something in there, it just makes more bumps. So that's the first thing. But we're going to also need a sine of 2 pi 3 times time. So we also need, you know, sine of 2 pi ft, where f is 3 and t is the variable. So that's also 3. And so again, we're going to have 3 sines now. So now the sines are going to start at 0 and go like that. So carefully draw 3 sines. Okay, so that's a sine. It looks just like a cosine. It's just moved over a little bit. You can see it just moved over a quarter of a cycle. So now we do our multiplication for every point in time. And so how do we do that? Let's do the, and here's going to be the output. This is our Fourier transform down here. And it's also going to have 2 parts. And so this is, we were in regular signal land, and then below this, we're in Fourier land. So we'll put a big dividing line there. Okay, so this is Fourier, and Fourier land is going to, which is this thing here, is going to have you know, so this is h. So that's after we transformed it from the small h. So that's the h real part. And here's the h imaginary part. So we're transforming two numbers, of which the first one always happens to have a 0 for the second number, into two numbers. So how do we do the multiplication? So we just take a point in time, like right here, and then we go down to the cosine and just multiply it. It's just a real multiplication. So this is, you know, just a real multiply, just a regular multiply. 2 times 2. So we just multiply that, and then say this is 3 down here, okay? Frequency 3. So this is, so we're now in frequency land. So there's frequency. So we multiply this guy times that guy, and then send it down to add it up, and then we multiply all of them, but I'll just draw a couple. Multiply this one times whatever the cosine is at that point, add that together, and then we, you know, multiply this one times that, add that together. So you can see it's a computationally intensive thing, because we essentially have, for each frequency, we've got to go to every single time point. Add that together. And so what do? Sum those up, and we get one number. And what that one number is effectively how much does this signal across all this time correlate with the cosine of 3 bumps. So that's the meaning of the real part of the Fourier transform. How much does this particular signal correlate with a cosine of 3 bumps? And it could be positive or negative. If it looks like an upside down cosine, it could be negative. So that's good for the first part. Now how do we do the, so that was the first part of the multiplication that we're doing here. So how does the second part work? Well, you just take that same number again, and then instead of correlating it with a cosine, just correlate it with a sine. And do the same thing over here. Just take the same number, and instead of multiplying it by a cosine, just multiply it by a sine instead. Same for over here. So skip the sine, go to cosine, same for over here. And then sum the whole mess up. This is, I'm just sort of doing 4 of them, but you got to do, you know, hundreds of them. Sum the whole mess up. And you get another sum. Come around this way. And one more. Okay, so sum all those up, and we get a second number. Also at frequency 3. So this is, and this number could be positive or negative. Let's just make it smaller. Okay, so this is another sum. We just added those guys up. So that's the Fourier transform. That's all there is to it. You're just correlating with a sine and a cosine. Now, why does that work? So the main reason it works is because, I mean, so first of all, why are we doing 2 of them? It seems like we just need something correlates with something. We should just sort of need to correlate it with one of a kind. Like, why don't we just correlate with just cosines of all different frequencies? And we'll talk about this next time, but the amazing thing about a cosine and a sine is they're completely uncorrelated. 0 correlated. So what does that mean? That means if I just go and take this value of cosine and multiply it by that value, and this value multiplied by that value. If I just do that across the entire sine and cosine, sum the whole mess up, I get 0. So basically, a sine and a cosine, if I sum that whole mess up, it equals 0. So a sine and a cosine are completely uncorrelated. But what that means, and you could say that, if you would say that in mathematical terms, they're orthogonal, at right angles to each other. Their dot product is 0. Same thing. That's another way of saying the same thing. The dot product of this vector of all these cosine values and sine values, if we just multiply each pair and then sum the whole thing up, you get 0. So that's great, because that means that those two correlations with a cosine and a sine are completely at right angles to each other. They don't interfere with each other. So if you figure out how much the signal correlates with a cosine, it doesn't tell you anything about how much it correlates with a sine. It's completely independent. So and it turns out not only are cosine and sine at a given frequency orthogonal, completely uncorrelated, but all different frequencies are uncorrelated with each other. So frequency 2, it's like if you do frequency 2, like here's a sine of 2, is completely uncorrelated with frequency 3. Just magically, like you multiply all those numbers up, they exactly come out to 0. So all different frequencies, and then also sine and cosine, are completely uncorrelated. So what does this thing that you get out tell you? Well, it tells you how much it correlates with a cosine and a sine, but there's another way that you could do a Fourier transform. So this is kind of like the slow Fourier transform. You've probably heard there's something called a fast Fourier transform, FFT. This is how you would do it there's a tricky way of doing the Fourier transform that's much faster than doing it this way. But it's doing exactly the same thing, but it's just a tricky way of doing it. And so this is like the slow Fourier transform. How would you do I always say this, how would you do a really slow Fourier transform? So just to sort of get a concrete idea of what a Fourier transform does. Well, what you could do is you could take a cosine, correlate it with your signal, and then take a cosine that's slightly moved over, like move the cosine over just a little bit, like that. Just move it over just a smidgen, and then correlate it again. And then just move it over just a little bit more. So just move it over a little bit more, correlate it again. And keep doing that. Do it a million times. Keep doing that until you find the one that fits the best. So you'd have to move it. You'd have to move it through 360 to find until you start to repeat until you find the one that fits the best. That's exactly what a Fourier transform does. It finds the best fitting offset for 3 bumps, but it does it just by doing 2 correlations. And why is that? Well, because those 2 correlations are completely uncorrelated with each other. And so they're kind of you can think of them at right angles to each other. And so it only takes 2 of them. You just correlate with a sine and a cosine, and from that, you can basically calculate what the offset is. That's the phase. And you could do the exact same thing if you just took that single cosine and tweaked it over and then did all the correlations, and find out what's the one that gives us the biggest correlation, the biggest sum. You could get exactly the same effect just by doing that. But this is really cool and efficient. We just correlate with the sine and the cosine, and that dumps out the best fitting offset. So it's kind of hard to see that thing is an offset. And so typically what you do is you take, so if you're in MATLAB and you take a Fourier transform, you'll end up with a whole pile of numbers. And so this will be, the real and the imaginary numbers. So here's our Fourier transform. And so we'll get two sets of numbers, okay? They won't necessarily, be constrained to be, anywhere between, well, they could be anything, could be like 1,000,000, could be a large number. So that's our Fourier transform, but we typically don't look at it that way. We typically look at it converted into polar coordinates. So, and if you go back here, that's polar coordinates, that phi angle, that's the polar coordinate view, not the cosine and sine view. And so what are the polar coordinates? Well, we take how do we convert to polar coordinates? So we've got some complex number, and here's the imaginary part of it and the real part of it. So what we want is the polar coordinates. And so what is the amplitude going to equal? It's just going to equal Euclidean distance. So it's just real squared plus imaginary squared, square root of that. That's how we calculate the amplitude from this real and imaginary number. And then how do we get the angle? The angle is, going to be the angle whose tangent is the following. That's the function that you would use if you're in MATLAB or C or something. So whatever. So that's going to be this. That angle there. So, but what are you doing? You're just converting this x and y into an angle and an amplitude, just polar coordinate conversion. And so once we've done that, what do we end up with? So we end up with these. Remember, this is all frequency. So we're in frequency land now. So this is all we did was we took these two guys here and moved them up here. So we're in frequency land now, but now we're going to change over to amplitude and phase land. And so this is typically what you look at. If you're looking at an MRI image, you're looking at the amplitude image. And so what is the amplitude image? The amplitude image is just take these two values at each point here and then run that operation on them to find out what their amplitude and polar angle is, and then you get a set of amplitudes for the first one. And so say, you'll get some kind of spectrum like this, something like that. And so what does that mean? That means for each frequency, there's going to be a certain amplitude. So say there was a lot of 3 bump. So say that was 3. Say the signal looked a lot like 3. And then it didn't look like 4, didn't look like 5, and maybe it looked like 8. So it looked a lot like 3 and 8, and then there was some noise up here at, say, like 97 or something like that. 97 bumps. So that's the amplitude. That doesn't tell you what the offset of the best fitting sinusoid is. But the phase angle does. And so the phase angle will go from, like 180 to minus 180. And so there's going to be a phase angle that you would calculate here that will go in between 180 and minus 180. And so for that, if you look at, it's also a function of frequency. So this is still, there's still 3 here. So this is frequency again. And so if we look at this peak in our amplitude, meaning there's a lot of 3 bumpiness in our signal, we could look down to this number, and that will tell you what the offset is. And that could be, say, like 180 to between 180 and minus 180. And so that's the meaning of this. And so this is, this guy is the phase, and this guy's the amplitude. So what's kind of the bottom line? So the bottom line is for a real signal, it's a little more complicated with a complex signal, but for a real signal, the Fourier transform just equals, is equivalent to to correlating with cos and sine at each frequency. Each frequency. So you have to do that correlation for each frequency across, each across time. Each across all time. So that's the meaning of the Fourier transform. Each across all time. So that's the bottom line. So that's the way you can begin to just sort of get a feel for like what is the Fourier transform actually doing. Now, interesting thing about the Fourier transform is that once you've done it, if you do another Fourier transform on your output, you get back to where you were before. And at first, when you hear this, it seems impossible. So I just did this. I just correlated with sines and cosines. I got a signal. I correlated with sines and cosines, and I turned it into this complex Fourier transform frequency domain. So this is, this is time, and then frequency on this side. Freak. So we turned our signal from time into frequency, but then if I just take that frequency signal, this thing here, and correlate that with sines and cosines, I get back to the signal. I can completely reconstruct the signal from that. Exactly. Reconstruct the signal by just doing another Fourier transform on this thing that we just Fourier transformed. And you could sort of see it's got a certain symmetry to it. Like for each frequency, we had to go to each point in time. And then when we do the opposite inverse Fourier transform, it's exactly the same equation except for a sign change. All we do is for each time point, we go to every frequency and do a sum, and then it gets back to our time signal. So it goes two ways. So the inverse Fourier transform is just the exact same thing. It's just doing the Fourier transform again, essentially, and then you pop back to time if you're in frequency. So last but not least, how is this related to MRI? Why do we want to know about it for MRI? So basically, how does MRI work? Well, we fiddle with gradients to make signal that is Fourier transform of brain. So that's fundamentally what we do. And then we just inverse Fourier transform it. ft minus 1, that's the inverse Fourier transform. So ft minus 1 it to get image. And that gives us our image. So what's the difference? What's the difference with MRI? Well, with MRI, we're dealing with, instead of time, we're dealing with position. And instead of frequency, we're dealing with spatial frequency. And so that's usually called K. So that's why it's K-space. Because if you're doing sort of spatial frequency instead of temporal frequency, we'll call it K. But it's exactly the same operation. And you can sort of see why it makes sense to have a coil that's recording the output of the entire head. That's actually a good thing because we're going to have to sum across all x instead of sum across all t. And so this whole the Fourier transform is actually physically performed by the gradients and the RF coil. And then it's doing a complex add the coil is doing, it's the coil, the RF coil, because of the phase-sensitive detection, is doing a complex add. And it's doing a complex multiply. So it literally is exactly doing a Fourier transform of the brain by fiddling with the gradients to collect all these data points. We'll go over it in much more detail to essentially end up with a Fourier transform of the brain, and then we just inverse Fourier transform it. Okay, so if this is the first time you've seen the actual Fourier transform, it's always a shock to see it the first time. Some of you have been through it before, but this is a way of sort of thinking about it as just correlations with sines and cosines, which are themselves completely uncorrelated with each other. And so it's a good way, it's an upstanding way to break up our signal. We break up our signal into a bunch of things that are not correlated with each other. So they're like independent components, very much like independent components. They're sort of all at right angles to each other, so they're not correlated with each other. They're independent from each other. Okay, any Fourier questions in the last -5 minutes? So it's a fearsome equation with all these things all in a row, but you can sort of glom them down. So like, that whole mess is an angle, and then that's just like this angle here, and that just turns into a sine and a cosine. Yeah, I mean, my first reaction when I saw that, I sort of knew how Fourier transform worked, that it turned it into frequencies. But then when I looked at this, I just said, nah, no can do. But it turns out to just sort of be sines and cosines. Okay, any questions? And then, once you sort of know how it works, you don't have to bother with this. You just go into MATLAB and just go FFT and it just does it all for you. But it's good to know what it's doing. Okay, well, we'll continue with the Fourier transform for the rest of the week to try to sort of hash through it.